First of all, I would like to thank the organizer for invitation to such a traditional conference, which I am first time to be a part of. Uh, as Alberto said, my name is Jiri Vondrasek. I'm from Institute of Organic Chemistry and Biochemistry, and I'm also the head of Czech infrastructure for biological data, which is ELIXIR. And I think I will present today something like a view from some other side, from the research side, because my role at the institution is like a PI and someone who has to find out where is the interface between different fields of the research. Very shortly about the IOCB Prague. It's a research institution in the basic research, but I think most of the things we are actually now devoting to the interface between the chemical and biological sciences, and also translational result for the application. And in the past, we were quite, I think, lucky and successful, because one of the patents of the drugs synthesized by our institute led to the license from the Gilead scientists, which is an American-based pharma company. And from this revenue, I think we can actually we started to build up the first-class institution within the Czech Republic, and we believe also in Europe. So we have about 1,000 people working there, about 40 nationalities, and we have a 51 scientific group, which my group is actually one of the senior research group at the institute. The reason why we actually ended up with the semantic is not complicated. I would like to show you something which I've been thinking about yesterday during the walk back to the hotel. During the lectures and during the tutorial, I noticed that there are some similarity between the way how we are thinking and between the way how the semantic web and all that, I would say, infrastructure around the semantic web is actually remind me of the way how we deal with the question. So the first thing is that the way how we formulate the question shape the conclusion we reach, and also the reasoning is inherited, guided by the structure of our inquiries, which means that we are part of the process where we still are thinking in certain, I would say, limits. We are still doing something which is consequentially connected with each other. So, for example, if I've been asked the question for where I'm, I don't know, in my research, what I am supposed to do. So first of all, I have to really connect the things which really interest me with the reasoning which I have basically in my research history. So I see the semantic web very similar, because it links the structure knowledge, enabling inference, and facilitating interoperability, which is the core. The interoperability is something what we are looking for in the basic research all the time. It's not easy at all, because this is all the principle how we would like to get the information from one side and utilize it in another side. So getting some knowledge from the chemistry and utilizing I would say the structural biology, or probably in the medicine or in the healthcare. So the way how we connect the facts, how we derive the meaning, making the natural extension, means to be that this is something what we would like to actually pursue and have in the life science, where the data integration is critical for the discovery and decision making. That means that this is something which should be present during the way how we actually conduct research. And if there are the concepts where we are quite sure that they reflect the reality, then we should actually follow the path which is actually then drafted by that things. So first of all, I'm not sure how many of you heard about the ELIXIR. I don't, yeah? Great. Tim Hubar will be pleased. So the ELIXIR is the intergovernmental organization which are bringing together resources from the European countries. Now I think we are 24, but we are basically focused on the building up the robust infrastructure, having the databases, making the software tools which are standardized or also benchmarked, training resources, and last but not least, the interoperability resources. So this is something which is closely related to the subject of this meeting. ELIXIR also have the facility when they can conduct computing in the, let's say, biological data. And last but not least, we started about 10 years ago with data management support. And I'm pleased that it will be the Netherlands and the Czech Republic where they came with the concept of the data management. So we are trying to build up the life science informatics capacity and infrastructure within the Europe, but mostly we are relying on the network experts. So this is something when the knowledge could be transferred very easily, because we know probably very well how the structure of the knowledge can be transferred. And also we have I think, a portfolio of really high quality services and resources, which are available to all. So it means there are open resources. And this is very important, because the next few minutes I'll be talking about that open data or open resources, which I think they are very much of interest of this community. Well, okay. What the data management is a challenge in life sciences. I don't know how many of you are part of the scientific group. They deal in their daily life with the data, with actually interoperability of the data within the certain field. But think as that we are facing the very, very much problems. So first of all, the data growth. As you know, with all the new sequencer, new generation sequencing, all the data from the mass spec, cryo-EM, they are producing enormous amount of data. And the data should be somehow very well, I would say, managed and also stored. But sometimes it seems to be that if data doesn't follow certain standards, in the future, they could be probably very, very much useless. So we are also trying to catch up with the data diversity, meaning that we really have to somehow try in the life science to connect the different fields, different disciplines within the framework, which is clear for the researchers how to deal with it. The problem with data location is, I think, mostly for the data which are by the character sensitive. It means healthcare data, which they have to stay at the same place where they were actually recorded or created. And the data sensitivity is, I think, a big problem, which is, I think, solved on both sides of the barricade. I mean, from the informatics point of view, as well as from the governmental point of view, which we would like to actually keep the data aligned with the principles of the anonymity, and also doesn't provide something like a hole within the system for the data to be misused. So the thing what we are doing within the ELIXIR infrastructure is that we actually exchange knowledge between different disciplines. And this is not easy, because as you can see, the many of that resources were created without the concept prior to the ELIXIR, or prior to any kind of the consortium that people are actually starting to build up. So the first, I think, first attempt how to deal with the data was the set up something what we call ELIXIR core data resources. So the core data resources, they are fundamental importance for community, and we have to have a long-term preservation of that data. So there's a process where we are actually identifying that ELIXIR core data resources. It involves careful evaluation, multiple facets of the data, and indicators which are used in the evaluation can be actually summarized in a few categories. So first of all, it's a scientific focus and quality of the science. So must be something which has really, I think, a strong track record. It's used by the community and has a standards and has everything up to the sustainability. And must be community served by the resource. Must be community which is dedicated to the resources which are then part of that core, and the quality. So we have about 5, as I said, criteria, including the legal and funding infrastructure, which is not easy, because most of the data core resources are actually funded or were funded by the countries or the science foundations, not internationally. And last but not least, we would like to see how the data are actually impacting to the translational stories. What I'd like to show you now, I don't know if that I wanted to show you that what are the core data resources, how many of them are. It's including UniProt, PDBE, including the Swiss Prot, and these are about the 23 of data core resources within the ELIXIR infrastructure. So the people who are taking care about them are also guaranteeing that there'll be sustainability at least for the 5-10 years. So which is not easy. If you see the funds, how they are cut it for the research, it's not easy to actually keep that quality of the resource at the high standards. There are also ELIXIR deposition databases. It doesn't mean that they are not important, but they are more like focused on the certain field of the research. And this is something what we would like to also keep in the future as the data resources. One of the things I would like to tell you about this is they are of different kinds. So they are not all the time the same format. They are not dedicated to the semantic treatment. We cannot say about the interoperability in a semantic way. We try to be as interoperable, as much interoperable as possible, but this is not guaranteed. The thing is that we are trying to have links from the different resources in a way where all that creators are actually checking very carefully how that interoperability is guaranteed, but you cannot actually approach all of them by, for example, the SPARQL queries. So there is a question how to go further. And I think probably all of you saw that Wikipedia page where we are following the definition of the linked data, which are something what we are looking for. I mean, from the researcher point of view, you are always looking for the data which have something in common, that you can connect within the framework you are working at. So we call the linked data the structured data, which is interlinked with the other data, and they are become useful by the semantic queries, as for example, web technologies like HTTP, RDF, and URI. So if I can quote it, Tim Berners-Lee, so there are 4 principles of the linked data. First of all, has to have a uniform resource identifiers. HTTP URIs should be used to allow these things to be looked up, interpreted, which is something which I think is natural for you, but not for all the people who are actually looking for the data which could be linked. And last but not least, use for information. What name identifiers should provide through the open standards, like for example, RDF and SPARQL. And when publishing data on the web, should be the things referred as the HTTP-based names. And this is a diagram where you can see the clusters of the, I would say, linked data within different categories. So when you look on the life sciences, which is very linked with the Wikipedia data, you can see also the publication and other clusters. We would like to actually get that connections quite useful for everyone who is working in a science in a context larger than the field. So the other approach is can we look about the linked open data? This is something what we are really interested about, because at the ELIXIR we are providing the open data. So they are data we are released under an open license and doesn't impede their use for free. So how we can actually compare now that criteria, which you can see here, which is the 5-star linked open data criteria, on, for example, the ELIXIR data core resources. So how many of them are of that kind? So I went through that ELIXIR data core resources. So all of them have a 1-star, all of them have a 2 stars, and all of them have a 3 stars. But there are data, only a few of them has a 5 stars. So it has a W3C standards using RDF and employing query. And this is the work we are actually working. As a scientist, you don't really care who is providing data. You care about the quality of the data and the interoperability of the data. All the times you are really kind of attracted by the way how you can use your I would say, data in your research, how reliable the data is. And so in comparison with the ELIXIR data core resources, these are linked science open data in life sciences. So these are data which are known, has to have the project, and there are examples of the RDF graph and description for certain kind of, I would say, the data repositories. So you can see that there are several processes like a drug bank, KEGG, Farm GKB, and CTD, which is a project at the BioRDF. We have I think, a project at EBI, it's an EBRDF. We have a very unique project, UniProt, on proteins and data characteristic, and many, many others. The thing is that these are linked open data in the life science. I would like to have the concept how to use them together, how to actually find out a way the data can actually talk to each other, and how we are actually approaching the data, and from the semantic point of view. So this is something we can start with. And as I said, there's an infrastructure. It also has ELIXIR data core resources. Some of them are part of these life science linked open data. But the thing is that we don't know how to actually make them together interoperable and effectively used by the community. I think it's very nice to for the, I would say, the people like scientists and informatics, how to deal with that formats and the features. But for the everyday life of the researcher, it's really hard to find out if there is an efficient way how to get to the data and how to get the information from the data for the everyday work. This is something which is extracted from that life science linked open data cloud. So you get all that things which you can then extract by the extractors like URE, ontologies and stuff like that. And then you can construct a graph. So this is the meta-analysis of the life science which are available on the web. So if you can do that, so if you will actually do the analysis on the previously shown, the table, you can see that there are certain kind of the clusters, and they actually make the available for you the connection between different kind of the project and different kind of the data. So the PDB is the structural data, and the EBI RDF, this is the consortium that's providing the RDF from the European Bioinformatics Institute. You have the Bio2 RDF, and you have UniProt also as a part of that network. And the thing is that within that space, I think the researchers should look for the connections, actually looking for the answers on probably very complicated questions. And the way how we actually do that question actually depends on many, many factors. And yeah, this is something which I'd like to stop a bit with, because the FAIR principles, which all of you know, are something with this, what is a nightmare for researchers. Because once you actually ask for a researcher, makes your data fair, they would ask you which way. I mean, how we could do that. I mean, in our everyday life, so that findable, accessible, interoperable, reusable data is not quite easy as it looked like. If we look on that FAIR guiding principles, and this is the principles getting from the paper published in 2016, I think is a Wilkinson et al. And Baron Mons was that corresponding author. So you can find out there are many, many features and flavors of the what does it mean findable. Findable means that you need to have a metadata which are assigned and globally unique. Data should be described with rich metadata. Try to explain to the researcher what is the metadata. And metadata clearly and explicitly include the identifier of the data it describes. So the findable means we have to have something like a label where you can find out upon the request. Accessible, if the data are retrievable by the identifiers using standardized communication protocol, TCP, Protocol has to be open, free and universally implementable, allows for the authentication because you really have to have the access to the data, and the metadata also has to be accessible, even when the data are no longer available. And the track of the data should be stored somewhere. And then we come to the interoperability, because interoperability, this is the, I think, a background of the science when you try to find out relations, and something like I think everyday work for every scientist means that they have to combine the different resources for the picture. So the interoperability means that you need to have a formal access to the shared, and I think a broadly applicable language for knowledge representation. So you have to use the vocabularies that have to follow FAIR principles, and data which has to include qualified references to other metadata. If you read this and you are the scientist, I think you get confused up the second line. So what does it mean? How do practicals do that? So the reusability means that you can actually download the data from the other resources, must be richly described, and also released with a clear and accessible data use license. This is something what other people are also confused about. The license means there are the conditions for reusing the data for the future work. Data has to be associated with detailed provenance, who made them, where, which version, and stuff like that. And also, there are certain domain relevant community standards which has to be met. And I don't know if you remember the graph where I actually showed the ELIXIR. ELIXIR has 19 scientific communities which are different because they are different regarding the data, their format, the expertise, and stuff like that. So data meet domain relevant community standard mean that you also have something which then could be exchangeable within the different fields. So this is just, I would say, graphical representation, what we showed. So persistent unique identifier, metadata, and indexed as searchable resource, make them findable. Metadata, which are broadly applicable, used in language. Metadata used for vocabulary that follow FAIR principles, and metadata include qualified reference. The auto metadata means the interoperability. It has to have the connectors where you actually connect the data. The accessible, I don't know how many of you actually met some complication with accessibility of the data. It's not always easy actually to get to the data which are shared by the community. Open data means that you can see the license where you are assigned to. So you really have to have also the mechanism or infrastructure for authentication, how you get the data, how you actually identify yourself if you like to use the data, and also metadata which are available when data is no longer existing. So reusability, I think you noticed that in the last few years, there are so many papers retracted from the, I think, high impact journals. Because I would say this is something which actually makes the people much more careful about what they are presenting when they are actually writing in their papers. Because the reusability means that anyone can actually repeat your experiment or computational experiment and actually confirm that what you did is the correct things. So I think reusability in the last years, where you are supposed to actually provide your data to public repositories like Zenodo, or if you have institutional repositories, is kind of the prevention for the people actually to pour the data which are not, I would say, reliable and which are not, didn't went to the scrutiny of the quality. Okay, so then how can we make a semantic fair? So how we see what is a findable? So we have to publish ontologies in dedicated repositories, and we also have to have the minimum ontology metadata. Last but not least, unique IDs to identify concepts, relations, and ontologies. Very much I follow the tutorial of the SPHN, which I think this is actually how I can see the impact of that rules. For the accessibility, we need to use the simple API to provide access to ontology content. Regarding the interoperability, we have to, or we should use the common practice at syntactic level. So this is you are the community who are actually working on that common practices and rules, and common structure for concept and logic of the interoperability. Regarding the reusability, we can reuse existing related ontologies to avoid ambiguity. I think this is the kind of the danger which I saw in many or few of the lectures here. And we also need to provide rich metadata to describe the concepts. Well, what are the new opportunities? I actually went through that material from the first fair, which we actually can formulate like the new opportunities is the standardized ontology design based on expert-driven recommendation. We need to improve the discoverability and reusability. We need to reduce ontology development cost and semantic ambiguity, which I actually mentioned. If you'd like to improve the semantic interoperability, it actually enables the creation of multidisciplinary knowledge graphs, which I think this is something what we are, I mean, from the researcher point of view, are looking for. We need to have the easily integrate heterogeneous and distributed resources into one particular multidisciplinary knowledge graph. Also, there is a need to have the framework to analyze semantic usage and overlap, and also extend the capabilities of semantically enabled tools. Well, now I will go a bit deeper into the field which I started to work with about 10 years ago. It's a Cheminformatics, and this is about how we, from the chemical science point of view, would like to actually share the data. Because I don't know how many of you are familiar how the chemical entities are shared across the different resources, but according our experience, sometimes it's a real mess, because you have something which, from the chemical point of view, it's very simple regarding the description, how the chemical looks like, the physical chemical properties. But if the chemical seems to be useful in the, I would say, medicine, biology, anywhere, so it has the consequences. It goes to the completely different environment, and you need it through the one piece of the molecule, get connection with the others. This is the first approach which I think was done in Japan. You can see that they have a global repository, or I would say the data resource. It was a NICAG RDF. They were connected with most of that data providers regarding the chemical data, like a drug bank, zinc, Kebbi, molecules, and so on. Within that, they are available to do SPARQL searchable databases, like a PubChem or the Campbell. So they can soak the data from the different perspective. They actually went to the concept they created and actually tried to apply it on the projects in Japan, which were then connected with a concrete, I would say, problems like integration of the databases and substance searching system, which actually provide you the information about the chemicals. The thing is that this is very complicated story, because not all that resources are actually working on the framework which is, I would say, standardized. They probably, regarding that RDF resources, they have a very similar ontology. I think it's a Campbell ontology, Kebbi ontology, and DOI. And the thing is that in the future, we would like to actually get as much as possible just the connection between the particular chemical substance and the whole the biology up to the medicine. This is something like a goal we would like to reach. So if we look how we describe the chemical entities, this is something which I would say is a very classical way how we actually represent the objects of the chemical nature. So every molecule is created by the atom bonds. You have a connection table, then you can see connection and chemical structure, either in 2D or 3D. And then you have a molecule as a chemical compounds, which is described. And this is the properties, which has a physical, chemical, biological, toxicology, and stuff like that. And this is called like a substance. So it is composition, metadata, and ontology and fair. So this is something how we actually deal with a concrete molecule within the chemistry. And if you look for the classical data model, this is not a triple in the RDF way. So it's a structure, descriptor, and properties. You have everything in here. And then you go to the complicated world where you can actually have to choose between their different representation. So connection table, 2D coordinates, 3D coordinates, distance metric, and then last but not least, you get a linear notation and database IDS, which are SMILES, InChI, SLN, PubChem AD, and so on. It looks like that we have some kind of interoperability already inherited within that concept. So various structure of representation of benzene you can see here. So now you have to make a choice, which will be the representation you would like to use in the future. Because the thing is that you can actually share that, I would say, flag among the different resources. Try to find out a way how to semantically use it and how to actually find out what is the role of the particular chemicals within the structure. This is an example where there is a database called Ambit Nanomapper. They got as a nanomaterial and a chemicals database. They got a lot of resources, starting with a different spreadsheet, getting the data from the different stuff, and the result is the production of the data within the JSON, RDF, CSV, and many, many others. So this is the first thing what someone would try, at least in the nanomaterials and the chemicals, to actually do the stuff like a flow between the information you get from the particular, I would say, experiment or the description, and get them in some, I would say, conceptual framework. Well, there are many repositories which could be used in cheminformatics and chemistry. One of the, I would say, the most promising resource is the Chemotion. The Chemotion is the only repository which is semantically annotated. It's created by, I think, at the University of Karlsruhe by the consortium, where there are many, many other partners. Think means that this is a repository for samples, reaction, and related research data. There is something what we can find out as a connection between your particular kind of research if you would like to use that semantically annotated resource. I don't know who are actually using Chemotion here, but it's connected with Chemotion electronic notebook, which means that directly from the lab, you can actually download the data or upload the data to the Chemotion database, and it actually guarantees that the semantic way of the data record is the same. So this is one of the things what we would like probably continue within the chemistry, because not only that we have a lot large databases storing chemistry, which they are interlinked somehow, we would like to have the repository, which is, I think, from that point of view, really useful for the everyday chemist life. Well, there's a problem in the future. I don't know how many of you know about the Cheminformatics, but the number of the molecules we know up to now is only the part of the molecules we can generate. So it means you can actually create the new chemicals within the knowledge about just the chemical bonds and rules of the chemistry, but the part of the, I would say, the chemical words which we know now is about, I don't know, 5%. So we can generate new drugs, we can generate a new object, we can generate new chemicals. This is the first approach where you have that open GNUI, which are interactive and extensible source software for de novo molecular generation. Now, you can imagine there is no physical properties. There is no trace of any data about it, just the structure. But on the other hand, there is a request from the, I would say, the drug company, pharma company point of view. You'd like to have the new chemical. You don't know what part of that chemical words you'd like to use, but this is the neural network concept, which can help you to create a completely new molecule. And now you have the new chemical without any of that properties which you were actually able to track from the other databases. So we have a new world of the entities now here. And they are having the only purpose to serve as a drugs. And this is something which in the future will be probably a very problem, how to actually do it in a way, how they fit into that chemical space. Last but not least, there is a new company called DeepMedChem, and DeepMedChem is able to actually give you an orientation within the chemical space, how and where your molecules are, where is the density, how is the density of the molecules which are similar to your, and it's actually 1/2 billion scale search. This is really, really powerful things. Nothing to do with RDF, nothing to do with semantic. There will be enormous resources in the future. We need to somehow get them on a board to be able to somehow put them in the framework of the semantic treatment. And this is, I would say, something what we see as a kind of the problem we would like to focus on now. Well, now in the second part, I would like to report how we went through the process of the getting to know what is going on within the chemical space. So we get a strategy within the ELIXIR that we like to integrate a chemical data set with any resources using Cabby ontology, which I think is a reasonable way how to actually start with. As I mentioned before, there are ELIXIR core data resources. We'd like to actually make that interoperable with our database via SPARQL endpoints and make federated cross-database queries possible. We would like to also have the application to use a new workflow for automated drug design utilizing chemical information. So the interoperability can provide relevant information, can be automatically used for the in silico screening or large body of chemical information. This is connection with my previous slide. Last but not least, we need to have something like an extractor, getting that information for computational methods, interface with the proteomics, Cheminformatics, and also we need a very specific tools for proteome profiling. Let's start with the first one. When we actually, I don't know how many years ago, but we asked the question, can we put together all that Cheminformatics databases like Cabby, Campbell, DrugBank, stuff like that? So we tested the possibility how to merge the different databases. And Cabby, DrugBank, PDB, EChem, Human Metabolome Database, and PC, they are known, and some of them were actually providing the RDF. And for what we actually tried was the data we loaded into Oracle database as an RDF semantic graph. And the loaded data, we actually look on the InChI identifiers and also references to other databases, how they are interlinked. Every database which is in that list actually claim that the particular entity has the mirror in the other database under the same particular name. Well, so how to merge data sets? So if you look on that picture, so this is tautomer of one molecule. If you look on the name, it's different, so you can actually merge it by names. If you look on the smiles, you can merge it by the smiles. But if you do the InChI, then you can actually do that things. So InChI could be, or seems to be, like the universal way how you describe the tautomers of the molecule. And we would like to try out if that InChI, which was actually declared to be a part of every database we search in, if it's really have that power to identify the same stuff. Well, that's how we ended up. So we tried to map particular databases to each other. Just they claim they are linked. So if, for example, HMDB said that they have the same substance on the PDB-EChem, we try to link and then we compare the InChI. And as you can see, this is far from quality we expected. So between the KBA drug bank, this is the percentage of error, KBA HMDB, drug bank, PDB-EChem. It means that is a full InChI, including including the protonation state, isoform, and stuff like that. You get to this number. That's a very poor. You cannot just say that this is exactly the same entity within the different databases, although they are linked to each other, saying that they are the same entities within that. So based on that analysis, we were kind of afraid that there will be not easy way how to proceed further. And in that second round, we also asked the question how to represent the results, the SPARQL results, when we actually asking that databases, which we actually put in the RDF form. So we would like to have the user-friendly representation of SPARQL results, but IRI seems to be not very friendly for that, because entities are associated with templates without generating the visual representation. So we employed Apache velocity templating system, which was extended with a SPARQL query support, and that was the result. We switched the OpenLink Virtuoso for better performance to get that thing regarding that queries, and the results quite useful for the people who would like to do that. And then we were approached by the chemists, I mean, fellow chemists from the institution, that the most things they are care about is to look for the similarity compounds of the structures. So, because if they are developing a drugs, they would like to know all of that, I would say, substituents, possibilities, and also probably the ideas for the new skeletons or stuff like that. And at that time, we utilized the OrChem chemistry plugin, which were developed for Oracle. So we could actually find out there is a graphical interface, it's open source, could be ported to Virtuoso. So we actually started to implement it into that first version of our database. So calling OrChem from the SPARQL is not possible straightforwardly. So we needed to write the translator from extended SPARQL to SQL with SPARQL fragments. And we succeeded with that. So there was a structure search integration. As you can see, this is something which is a part of the query. And we also ask for the, as you can see, the SageM query within that Smiles code. Well, then was one more step. So we would like to actually make that data integrated in a larger scale. And I think a larger chemical resource for this is a PubChem, which was supposed to be here, but unfortunately is not. So the PubChem is an order of magnitude larger than KEBI. It's 100 of millions compounds. But we found out that Virtuoso performance had some limits. And we actually a little bit experimented with many things. And so we came to the solution to store data in tables in the relation database. So we needed to convert the semantic data to tables. We need to write, we need to write a mapping tables back to semantic data. And the performance depends on the structure of the original data and the relational scheme. So now we were kind of forced actually to convert the semantic data to the tables, actually do the mapping of the tables back to semantic data. So it looked like it's complicated, but it wasn't so bad as we expected. Sorry. Too fast. Okay, this is an example of how we integrated big data. There's a representation how we have for two examples like the journals and the papers, the schema how we are actually putting the data in, and here is the same within the tables. So now we have to have kind of decision which way we will be going for the next period. Seems like the most, I think, a hard decision was to come from decision not to use the Virtuoso and going to the Postgres SQL database. So as you can see, we started with the RDF, and all of a sudden we actually decided to make all the RDF to tables, and also the query of the SPARQL actually wrote in the Postgres and asking over the Postgres database. So the Postgres was selected as the base, and it's not semantic. So we need to also write, SPARQL to SQL translator. And this was the final solution what we made. So based on the existing translator we already did for extended SPARQL, as I showed you before. So my colleagues actually did most of the things from the very beginning up to the, I would say, the successful end. So the switching to Postgres SQL, here you can see the performance, how we can actually compare with the different engines like Virtuoso. This is the IDSM SPARQL engine, which is source. So we don't perform too bad. And the thing is that most of the other engines actually perform worse than we are. We were not completely satisfied, but on the other hand, with most of the complication we had with the Virtuoso, we decided to go this way. Well, then there's also the part of the search where we already relied on the ORCAM. As I said, ORCAM was a part of that Oracle database search system, and my colleague, Mirek Kratochvíl, suggested to come with our own, I would say, the chemical plugin. It's called CHIM. So the ORCAM needed to be rewritten for PostgreSQL. So most part from the Java as rewritten to C, and overall speed up was by several orders of magnitude. So it used a full text index. So select low number of candidates. You can see now that how we actually have a compound, how we index the compound, how we actually do the query, and the Apache Luce as the engine for the searching. Okay, this is the interface of it. So as you can notice that there are few options. First of all, you can make the search within that all the database I showed you, either separately or all at once. You can also choose the graph mode. Also, this protonation state, isotope, stereochemistry, and tautomerism. This is free of charge. Is implemented on our IDSM GUI, and it's a very, very much used by the chemist. This is the first, I would say, the answer to the people who came and would like to know what is the chemical structure similar to mine, which I'm going to synthesize. Okay, and to our surprise, the CHIM performed quite well in comparison with others. So RDKit, ORCAM, and the others. So over the CHIM Luce, so you can see that that was I think the best performance we do it. So we have now I would say the very, very good tool for looking for the structures within the chemical space, even better than some of that plugins which are developed, and they are also either part of the free of charge or part of the commercial solution or the free of charge. And this is all called integrated database of small molecule, which are now currently integrates the PubChem RDF, Campbell, Kebi, Mona, ISDB, Drug Bank, and Wikidata, only the structures. So we have about 120 million compounds and about 30 billion virtual triples stored and performed. Thing is, that this is the interface of that SPARQL GUI, which we have now. We have kind of the templates when you can actually use it as an examples. If you are not familiar with the SPARQL, we are now have a collaboration with our Belgian and Swiss partners about how to actually write the SPARQL query even for the chemists. It means how you can formulate your query and then actually rewrite it to the SPARQL query language. So this is the interface we are presenting on our integrated database of small molecules. We are not new repositories. We are not data provider, but we can actually find out the way how you actually connect the data of the chemicals, how you can query them, and how you can use them. So last but not least, we were also approached by the people from the mass spectrometry. And mass spectrometry has a very similar problem like in the chemical compounds. Now you have to find out the way how you can compare the two mass spectra. And support the mass spectrum similar to search mean that we are actually relying on very similar structure as we did for the SHM. It's based on the MatchMS project. So it means that there are some components and also employ semantic integrated ontology SEO within that. So the structure you see is here, where you have an experiment, you annotate it, you have a spectrum, and also you can actually find out where the compound. So we now have the tool when you actually will upload your mass spec. If you are able to find out, you are now able to find out a similar mass spec within the mass spec database. And then we have also the comparison with the chemicals which are produced by that mass spectroscopy data. This is what we would like to find out in the future, how useful it will be for the people combining, for example, in the metabolomics, identifying new compounds in the chemical space, and so on. I didn't mention that phase, which are now, I think, very intensively performed or pursued by our team, as a federated queries and federated query support. I think this is very, very useful part of the SPARQL because, however, there are few problems because even the evaluation of that federated query actually is a problem. We are currently working in cooperation with SIB and Ghent University and the solving that problem, and we'd like to also I would say contribute to it, to the federated query debugger. Marek Moss from my group has a poster on it, so I don't know if some of you actually were at his poster, but I don't know if their posters are still there, so you can take a look on that. So this is the federated query example, how we are actually logically going through the query. So for example, if you like to select cholesterol or cholesterol derivatives within the IDSM, you would like to find out the reaction which are involving these molecules, select the proteins that catalyze the reaction, and select molecule that inhibits the catalysis. So you are approaching different resources. And via the federated queries, it's possible to get the answer, which is, I think, quite nice demonstration of the power of the interoperable thing. I see Alberto is standing, so I would like to only very briefly say that these are our partners. These are members of the consortium, ID Lab in Ghent University, and Vital Swiss Prod and Dismos Group at SIB. And shortcoming of the SPARQL system that cannot easily include querying over private unpublished data, lack of documentation, federated queries, and difficult to evaluate, and accessing data is not for non-SPARQL users. I don't want to go to that details, but solution is, first, University of Ghent will do solution for the storing private and public data in solid iPods. We will optimize the federated queries. We will also create a tool to monitor evaluation of federated queries. RDF documentation will be up to SIB and University of Ghent, and integration of pods and SPARQL accessing the ecosystem also at SIB. So I think this is the list of predicted bioremediators. Just I think, the representation of the workflow. But last but not least, I would like to acknowledge all of my colleagues which were working on that project for a long time. From my lab is Jakub Galgonek, who is the engineer who is behind all of that things, movements from that RDF to Postgres and back, and developing SageM and stuff like that. If you really would like to get details of the work of my group, so connect with Jakub. Mirek Kratochvíl, the guy, he's now in the Luxembourg, is behind the SageM. Marek is another part of my team, which is working now on that tool I mentioned. And Honza Balázsek was the student of mine who actually finished. I would like also dedicate my thanks to CHIST-ERA team. So starting with Jervan, and I would like to also mention that there are many, many people who are still and pretty much in productive atmosphere of the collaboration. And last but not least, thank you for your attention.
Thanks a lot, Jiri, for this beautiful presentation. So I'm wondering, so we are in this group of NFDI for Chem. So you mentioned the ChemOcean, and I'm also a representative of NFDI for CAT, so for the catalysis part of this. And we're discussing going beyond the substances, going to the reactions. Mm-hmm. And we're discussing how to represent reactions in a semantic way. And there are very, very diverse opinions about that, because some of them just need starting material, conversion, procedure, and then the final product. Others need like quantum representation of the energy levels of the different states, because it's important for the reaction coordinates to really predict things. So you need very different granularity of the representation. And to my opinion, semantics can't capture these details. So what is your, in your environment, the current opinion state about this representation of reactions with semantics?
The thing is that we actually discussed that with our experimental chemist colleagues. So they are for the first way you mentioned, just to put the amounts and the reaction and whatever, the physical chemistry things. And I don't know if it's all, but if you would like to actually include also kind of the quantum chemistry or whatever kind of the computational approach to it, I'm not sure if it works, because this is not always clear if the description by the, I would say, the computational chemistry actually represent the reaction properly, because they are kind of the iteration. So I would probably prefer from the very beginning only to gather the information regarding the reaction in a classical way, but still there are some limits, because the people don't use the same, I would say, the standards. They really have to have something like I would say the standards which they are not agree with. I think a solution would be the ChemOcean electronic notebook, or any electronic notebook which is dedicated for the chemistry, because then you can have that, I think, reaction actually properly written and also annotated by the metadata. But I think this is only way where the chemist or the fellow chemists from our institute were, I think, willing to spend the time to think about it.
Thanks for your talk. It's actually fantastic, all these developments that you've described. I have a question about, you're talking about the different data that you're sharing in the network. Are you also sharing metadata about services? So you're talking about, for instance, FAIR, you've got different aspects of the data, accessibility, interoperability, discoverability, but then how do you measure these things? And for instance, if I go to an endpoint, how do I know what's there, how long it's going to take to get it to me? Will it take hours or days? That sort of thing.
Yeah. That would be ongoing work. We don't provide that. But this is definitely our next goal to do what just suggested.
Yeah, thanks a lot. I have a question to the first part of the talk when you introduced the ELIXIR core data resources. So at DSMZ, we have 3.5 ELIXIR core data resource, and I'm saying a half because LPSN is yet global core biodata resource, but not yet ELIXIR core data resource. To your opinion, what is the difference between those? What are the similarities, and should we still strive to become ELIXIR core data resources?
I'm sorry, I didn't understand other core resources we mentioned.
A global core
Global core
biodata resource?
You mean the table I showed? No.
No.
ELIXIR core resources are data resources which were actually identified by the ELIXIR board.
Yes, I know. We do have a couple of them, but yeah. What is the difference to the global core biodata initiative?
I don't know.
You're not familiar with it? Okay, thank you.
Hi, thanks for the talk. Quite interesting. And I'm just interested to know about your future plans. Are you planning to extend it to other chemical modalities like the biologics or peptides?
Yeah. So our idea was, first of all, actually to find out all the resources in RDF. So we find out that there are not so many, but now we are working on the concept that based on the, I would say, request of either our collaborators or our colleagues from the institution, we are gathering other databases and other information sources within. So the data plan we will actually present in our next paper or upon the request if you want.